This is your intro to equilibrium. This is the equation you will use when dealing with equilibrium. The concentration of C to the coefficient of C times the concentration of D to the coefficient of D divided by the concentration of A to the coefficient of A times the concentration of B to the coefficient of B. Here's an example to go along with it. A plus 2B yields 2C plus D. Since it's an equilibrium equation, there is an arrow going the other way too, for the reverse reaction. The example for this is the concentration of C squared times the concentration of D over the concentration of A times the concentration of B squared. The first thing you'll learn about equilibrium is Le Chatelier's principle. The first part about Le Chatelier's principle is about concentration. Here is an example of an equilibrium reaction. The Hb represents hemoglobin and the O2 represents oxygen. This is the equilibrium equation for the reaction. This equation represents carbon monoxide poisoning, which happens when a person has low levels of hemoglobin combined with O2. This shifts the reaction left, which causes for less oxygen. This happens because since the person lost HbO2, the reaction is trying to create more HbO2 to make up for the missing concentration it lost. To help someone with carbon monoxide poisoning, you give them oxygen. Increasing the concentration of oxygen shifts the reaction left, which creates more of the HbO2. The next part of Le Chatelier's principle is pressure. In this equation, there are 2 moles of H2, 1 mole of O2, and 2 moles of H2O. In total for the reactants, there are 3 moles, and in total for the products, there are 2 moles. If there is an outside force of an increase of pressure on a system, the reaction will shift towards the side with less moles to create less collisions of particles, creating a lower pressure. If there is an outside force of a decrease of pressure on a system, the reaction will shift towards the side with more moles to create more collisions of particles, creating a higher pressure. The third part of Le Chatelier's principle is temperature. This equilibrium equation is endothermic, so we put the plus sign before the delta H and the heat on the reactant side. If there is an outside force of an increase of temperature on the system, the reaction will absorb heat in order to bring the temperature back down. This is an endothermic reaction, which in this case is a shift to the right. If there is an outside force of a decrease of temperature on the system, the reaction will release heat in order to bring the temperature back up. This is an exothermic reaction, which in this case is a shift to the left.
Alright, this is potassium thiocyanate solution, and I'm dropping in iron 3 nitrate solution.
What is this one?
We added half a pea size of potassium thiocyanate crystals in one spot, and now we have to wait 20 seconds until changes occur to the solution. The potassium thiocyanate crystals dissociated into potassium ions and SCN ions. Increasing the SCN ions concentration in the reaction shifted the reaction right, which created a dark orange color.
Alright.
Okay, we're adding half a pea-sized amount of potassium nitrate crystals. And then just wait a second. We added potassium nitrate crystals, which dissociated into potassium ions and nitrate ions. These are both not in the equilibrium equation, and therefore had no effect on the color.
Yep.
Okay, now we're adding a 4th size pea-size of sodium phosphate monobasic crystals. And then we wait 60 seconds. We added potassium monobasic crystals, which dissociated into sodium ions and H2PO4 ions. The H2PO4 ions combine with the iron ions in solution, decreasing the concentration of iron ions, shifting the reaction left, creating a clearer color.
Now I'm adding 1 drop of the iron nitrate solution.
I'm adding a pea-sized amount of potassium thiocyanate crystals in a different spot, and then you wait 2 seconds. We added iron nitrate to the solution, which dissociated, creating iron nitrate ions. Then we added potassium thiocyanate crystals to the solution, which dissociated, creating potassium ions and SCN ions. This created an increase of the concentration of iron ions and SCN ions, shifting the reaction right, creating a dark orange color. This is test tube A, this is test tube B of the solution that we made. And then put solution B in ice water. Putting the solution in a cold ice bath makes the solution become a darker color than before. If it becomes darker, it means the equation is shifting right. Because the system is cold, the reaction wants to release heat to warm it up, making the forward reaction exothermic. Now we're putting test tube B in hot water bath at 70 degrees Fahrenheit. And we're going to see how the color changes. Putting the solution in a hot bath makes the solution become a lighter color than before. If it becomes lighter, it means the equation is shifting left. Because the system is hot, the reaction wants to absorb heat to cool it down, making the reverse reaction endothermic.